Thank you. It is a delight to be here. Once I get over jet lag, it will be anyway. And I'm really impressed at the turnout that so many people would come out on a night like this to do philosophy. So my topic is potential infinity. To begin then, beginning with Aristotle, almost every major philosopher and mathematician before the 19th century rejected the notion of the actual infinite. The actual infinite, for our purposes, is a collection which has more than finitely many members, right? Or more than finitely many parts, or whatever, right? They all argued that the only sensible notion is that of potential infinity, at least for scientific purposes, and then later in the medieval period, non-theological ones, right? Once God gets into the discussion, then you sort of have to rethink what you want to say about infinity. So in physics, Aristotle wrote, so to go back to the beginning, for generally the infinite is as follows. There is always another and another to be taken, and the thing taken will always be finite, but always different. Right? As Sir Richard Sorabji put it, for Aristotle, infinity is an extended finitude. Again, I'll try to explain what that means, well, to the extent that I can. I mean, that I'm not a scholar of that period, but right. Now, Aristotle, along with, this is what they did have. Aristotle, along with ancient, medieval, and early modern mathematicians, recognized the existence of certain procedures that can be iterated indefinitely without limit. Examples are the bisection and extension of line segments, and that's the sort of thing Aristotle's talking about in that passage. So if you're given a line segment, you can bisect it, and then you can bisect the remainder and bisect the remainder, and there's no limit to this, right? Now, ancient mathematicians made brilliant use of such procedures. For example, the method of exhaustion, which is a forerunner to integration nowadays, was employed to calculate the areas of curved figures in terms of rectilinear ones. Right? Now, what was rejected, though, would be the end results of applying these procedures infinitely often. So in the case of bisecting a line, right, if you did this infinitely often, what you would end up with would be a point, right? And points were rejected, at least in some sense of their existence, and infinitely long regions. That is a region that would be, we tend to think of like lines now as like the real line is, it's infinite in both directions, but that's what that would have been off the table, right? That would be an actual infinity, right? On generation and corruption, Aristotle writes, right, for since no point is contiguous to another point, magnitudes are divisible through and through in one sense and not in another. Oh, I should comment at the beginning that this passage really defies interpretation. So if you're not getting it right, you're not alone. Well, because all right. But anyway, since no point is contiguous to another point, no point is next to another point, magnitudes are divisible through and through in one sense and yet not in another. When it is admitted that a magnitude is divisible through and through, it is thought that there is a point not only anywhere in it, but also everywhere in it. Hence, it follows that the magnitude must be divided away into nothing, into just a set of points, right? For there is a point everywhere within it, so that it consists either of contexts or of points, right? But it is only in one sense that the magnitude is divisible through and through, insofar as there is no one point anywhere in it, and all its points are everywhere within it if you take them singly, right? So if you didn't get that, right? Well, if you did get it, then sort of raise your hand and explain it to me. But the idea is that you talk about a magnitude can be divided through and through. In one sense, that's true. That is, there's no limit to how many times you can divide it. But we should not conclude from that the magnitude, say a line segment, is just a set of points. Is nothing more than the points there, right? That it just consists of the points. Now, that is how we think of line segments nowadays. It's just a set of points, right? So this is sort of, that was sort of a major departure. But we'll get to that a little bit, right? All right. Now, closely related to the notion of potential infinity for Aristotle is that of potential existence. So for Aristotle, points, right? So I mentioned, so what are points just are for Aristotle the limits of, or the endpoints of line segments, right? And line segments, by the way, are just the edges of plane figures, and plane figures are just the surfaces of physical objects, right? So all that points are, first and foremost for Aristotle, are the endpoints of line segments. What about the points interior to a line segment, right? Which any geometer is going to recognize, right? For Aristotle, those are places where the line can be broken, right? But if the line is not broken there, then the point only exists potentially, right? So along with potential infinity, we also have what we might call potential existence, right? And the same goes for the parts of the magnitude generally. So as a continuous magnitude, the line segment has a kind of unity to it. There's something that holds it together, makes it one thing. And its parts only exist potentially as places, as things which could be broken out of it, taken out of it. Now, Jonathan Lear, a scholar of this period, argues that it is not the existence of iterated procedures that makes for an Aristotelian potential infinity. So he's arguing against the gloss I just gave on it, right? That really what's involved are procedures that could be iterated, right? The matter, according to Lear, concerns the structure of geometric magnitudes, right? So this is Lear. It is easy to be misled into thinking that for Aristotle, a length is said to be potentially infinite because there could be a process of division that continued without end, right? So it's easy to be misled to think this, right? Which is pretty much how I put it, right? So the way I put it, it's misleading, right? That's what makes for potential infinity is that you've got a procedure that you can continue without end indefinitely, right? Then it is natural to be confused as to why such a process would not also show the line to be actually infinite by division, right? And again, that's the point that Aristotle seems to be making there, is that you would think that if you can divide it, then why don't we just think of it as a set of points, right? Because that's what you end up with when you do all the divisions, right? It would be more accurate, again back to Lear, to say that for Aristotle it is because the length is potentially infinite that there could be such a process. Right? So again, it's the other way around, right? More accurate, but still not true. Strictly speaking, there could not be such a process of dividing the thing out until you're all done, until there's nothing left but points. But the reason why there could not be is independent of the structure of the magnitude. However earnest the divider may be, I'm also mortal. Even at that sad moment when the process of division does terminate, there'll remain divisions which could have been made. Again, modally, right? The length is potentially infinite, not because of the existence of any process, but because of the structure of the magnitude. All right, again, now we don't need to get into this, well, unless you want to, but if you do, you have to find someone else. This exegetical matter, right? According to Lear, a line segment is potentially infinite because there are infinite many places where it can be divided, right? So no matter how many times you divide the line, there'll always be some of the line left. So he concludes that Aristotle's thesis is that the structure of the magnitude is such that any division will have to be only a partial one, a partial realization of its infinite divisibility. There'll have to be possible divisions that remain unactualized. All right, so on either Lear's reading or the one that I gave, the one that's misleading, according to Lear, concerning iterated procedures, potential infinity seems to invoke modality, that is what can be done, idealized in an idealized way, and the activities of a perhaps idealized mathematician, right? So it involves what you can do, right? Now there's a closely related matter, right? It's generally agreed that Euclid's Elements captures at least the spirit of geometry during Plato's and Aristotle's period, even though Euclid was 100 or some years later, right, than, well, depending on which one, right? But even though Euclid was much later, it's generally believe that what's in Euclid was pretty much in the air already in the mathematical world in Plato's and Aristotle's day. Now, most of the language of the Elements of Euclid is dynamic. It talks about what a presumed idealized geometer can do, right? For example, the first postulate in Euclid is to draw a straight line from any point to any point, right? So again, the first postulate is you can do this, right? Here's something you can do, right? And the second one is to produce a straight line continuously in a straight line. So if you have a straight line, you can extend it, right? Or consider the infamous fifth, right? The so-called parallel postulate, although parallels aren't mentioned. All right, so again, this is a quote from Euclid translated. If a straight line falling on two straight lines, you can see if I don't have anything I can scribble on here, do you?
It's like a letter A.
Well, okay, so I did sort of have to make, all right, so a straight line falling on two straight lines, right? So you have two straight lines here, and then a straight line goes across them, right? That make the interior angles of the same side less than two right angles, right? So one line here, two lines crossing it, the interior angles on the same side add up to less than 180, 180 degrees, right? Okay. All right, so that's the hypothesis. The straight lines, these two, if produced indefinitely, meet on the side on which the angle's less than the two right angles. Right? So it's talking about, again, what will happen if you do something. Extend the lines, eventually they'll meet. Right? Right. Now, Plato, was critical of the geometers of his day. To go back, one generation from Aristotle, was critical of the geometers of his day, arguing that this dynamic language is inconsistent with the nature of the true subject matter of geometry. Right? So Plato complains about this. Right? Apparently, the complaint didn't take hold because, 100 and some years later, Euclid continued to write that way. Right? All right. So here's Plato. This is from the Republic. The science of geometry is in direct contradiction with the language employed by its adepts. Their language is most ludicrous, for they speak as if they were doing something, and as if all their words were directed toward action. They talk of squaring and applying and adding and the like, and we just saw extending, dividing, right? Whereas, in fact, back to Plato, the real object of the entire subject is knowledge of what eternally exists, not of anything that comes to be this or that at some time and ceases to be. All right. So again, this is a nice Platonic thought. Right, if you like those things. Right. Aristotle rejected that orientation, right, the Platonic one, and we suggest, the we here is, this paper is co-authored, I should have mentioned that. It's co-authored with my friend from Oslo, Øystein Lindeboe. Right. So Aristotle rejected the Platonic orientation, and we suggest the dynamic language employed in ancient geometry better reflects his views. Right. Incidentally, well, not exactly contemporary, but closer to contemporary, Hilbert's geometry book is not written the same way Hilbert's is. Hilbert's geometry book is not written the same way Euclid's is. Right? Hilbert actually uses the kind of language that Plato would have approved of. Right? So remember we had the first postulate for Euclid. What was it? Shouldn't have done this. Now I'm not going to find where I was. I'm going the wrong way? No, I'm going backwards. Right. Oh, no, you're right. I went back too far. Yeah. Right. Yeah, to draw a straight line from any point to any point. All right. So again, that talks about what you can do. In Hilbert's geometry, that axiom is for any 2 points, there is a straight line that contains them both. Right. So Hilbert's language is not that Hilbert was a Platonist, but it's Platonistically correct. That would be the language that Plato would have had the geometers use. Platonistically correct, that's PC. Right, right, right. All right, now where was I? Right. All right, so the matter of infinity is tied to this. All right, so for the dynamic language, I think better reflects how Aristotle thinks of these things, again, to the extent that I'm entitled to an opinion about this. And we suggest it's employed, the dynamic language employed in ancient geometry better reflects his views, right? And the matter of infinity is tied to this, right? For Aristotle, we never have infinite collections of points, objects, or anything else. We never have infinitely long lines or infinitely large regions of space or time, and incidentally in Euclid either, right? Whenever Euclid talks about line, that's always, in modern terms, would mean line segment. Because of the structure of the geometric realm, this is the reading that Lear doesn't like. But I mean, obviously, it's not a good reading of potential infinity, but he certainly wouldn't agree that the following is true. Because of the structure of the geometric realm, oh no, this is Lear. Because of the structure of it, we have procedures that can be iterated indefinitely, and we speak about what those procedures could produce, or what they will eventually produce if carried sufficiently far, right? That was the fifth postulate, right? It was a procedure, and it tells you what's going to happen. In holding that the geometric procedures can be iterated indefinitely, again modally, right? That is, it's possible, right? Indefinitely. Aristotle again follows the mathematical practice of the time. I mean, again, it's a principle in Euclid that you can do this. Well, Euclid's later, but right. This time, though, Aristotle is arguing in opposition to his major opponents. That is the atomists. So the major opponents that Aristotle is dealing with here were the atomists who actually rejected infinite divisibility, even in its potential form. Right. Now, there's two versions of, again, I know this from scholars that, so there's two versions of atomism. There's kind of a boring one, and then there's sort of a radical one that to modern mind seems kind of goofy. The boring one is that it's a thesis about physical objects, that they're smallest physical objects, Nothing that in Aristotle would contradict that, or nothing in geometry would contradict that. The more radical kind of atomism is that it's a thesis about space as such, that there are smallest regions, right? And that's what Aristotle's rejecting, right? That much in line, of course, with contemporary mathematics. What I find kind of puzzling is that, as far as I know, there really weren't any defenders of actual infinity in antiquity. So I wonder who Aristotle is sort of arguing against, right? But again, that's, All right. All right, so the atomists, at least the radical kind, would actually postulate there's a limit to bisection, right? You can start with a line, bisect it, bisect it, bisect it. You'll come to a point where you can't bisect it anymore, right? And Aristotle rejects that, right? All right. Now, so that's all for antiquity. Now, in views like Aristotle's were standard throughout the medieval period and the early modern period, up throughout most of the 19th century. You begin to see some, well, we'll see glimmerings of opposition earlier than this, but you see it sort of stronger here and there, like Bolzano is a clear exception, and then finally Cantor, but we'll get to that. But anyway, before that, before the late 19th century, with Bolzano as a rather prominent but somewhat obscure at the time exception, the greatest mathematical minds all insisted that only the potentially infinite makes sense. And these are among the best mathematical minds ever, right? Leibniz, Descartes, Gauss, right, as we'll see, right? So Leibniz, for example, wrote, it could well be argued that since among any 10 terms there is a last, which is also the greatest of these numbers, it follows that among all numbers there is a last number, which is also the greatest of all numbers. But I think, remember this is Leibniz, such a number implies a contradiction. When it is said that there are infinitely many terms, it is not being said that there is some specific number of them, but that there are more than any specific number, right? Which is kind of a potentialist kind of reading. All right. Now, the contradiction that he mentions here, so there might be a greatest of all numbers, there might be an infinite number, and then he says he thinks that implies a contradiction. The contradiction is probably, again, I got this from scholars, so-called Galileo's paradox, right? Which nowadays is we call Hilbert's Hotel. The idea that if you do have an infinite set, then it'll be the same size as a proper subset of it, right? Nowadays, we just think, oh yeah, that's just a feature of it, right? Get used to it, right? Deal with it, right? As it put. But up until then, the very same thought was thought of as a reductio ad absurdum, right? All right. So that's all right. So what was a devastating bug in the notion of the actual infinite up until then, right, is now a feature, right? Right. So it wasn't just the computer companies that took bugs and turned them into features, right? All right. All right. Now here's more Leibniz. We conclude that there is no infinite magnitude, from which would follow that there is not an infinity of things either, or rather, it must be said that an infinity of things is not one whole, or that there is no aggregate of them. Here's another one from Leibniz. Yet Descartes and his followers, in making the world out to be indefinite, potentially infinite, so that we cannot conceive of any end to it, have said that matter has no limits. And they have some reason for replacing the term infinite by indefinite, right? For there is never an infinite whole in the world, although there are always wholes greater than others on infinitum. It can always get bigger and bigger and bigger, right? As I have shown elsewhere, the universe cannot be considered to be a whole, right? And then Gauss. I protest against the use of infinite magnitude as something completed, which is never permissible in mathematics. Now, I should mention that, yeah, I think that's the end of the... All right, so for Gauss and Leibniz, as for Aristotle, and a host of others, that is just about everybody else, the infinite just is the limitless of certain procedures. No, or that follows from the structure of things. No actual infinities exist. The only intelligible notion of infinity is that of potential infinity, the transcendence of any finite limit. Now, I should mention in fairness that these gentlemen were not, well, Aristotle aside, but maybe Descartes too, but certainly Leibniz and Gauss were not completely consistent here. I mean, they were, after all, in the forefront of the rigorization of the calculus, and they were painting around infinitesimals, and never with a straight face, though. I mean, they're always a bit ambivalent about it. So they were actually sort of pioneers in the groundwork that actually led to the exception of the actual infinite, and they couldn't really avoid all that in their own work. So they weren't completely consistent in their rejections, or thoroughly consistent in it the way that maybe Aristotle was. Right. All right. So now to the present. Well, sort of the present. 1897 or so. Right. All right. So for at least the cases of interest here, that is regions of space, numbers, natural numbers, and the like, Georg Cantor argued for the exact opposite of all this, right? Claiming that the potentially infinite is dubious, right? Unless it is somehow backed by an actual infinity, right? So here we have everyone going up to Cantor. I wish I understood the history better. It's sort of like a sea change. Cantor comes along and he says that, look, I really can't make any sense of the potentially infinite unless there's an actual infinity that's underlying it, right? So here's a couple of passages. I cannot describe any being to the indefinite, the variable, the improper infinite, in whatever form they appear, because they are nothing but either relational concepts or merely subjective representations or intuitions, never adequate ideas of this potentialism business, right? This is the smoking gun. Every potential infinite, must be infinity there. Well, who knows? I mean, this is German, but every potential infinity, if it is to be applicable in a rigorous mathematical way, presupposes an actual infinite, right? Now, Oystein and I, Linnebo and I, think it's safe to say that this Cantorian orientation is now dominant in the relevant intellectual communities, especially concerning the mathematical domains mentioned above, with the constructive mathematicians as notable exceptions, right? So somehow Cantor got everyone turned around on this to the point now where people even have trouble seeing it any other way, right? People have asked me, colleagues and so on, what are you working on? Potential infinity, what's that? And then they'll actually echo, without knowing it, Cantor's line. Well, that only makes sense if there's an actual infinity underlying it, right? Now, I'll skip over this, but I'll gloss on it. It should be noted that Cantor himself was not completely consistent here. So Cantor's rejecting the potentially infinite for things like the natural numbers and geometric space and the real numbers and stuff like that. But at least at times when he wants to talk about the universe of sets altogether, he sort of starts to wax potential again, right? But anyway, that's a topic for a different day. Right. I mean, there's 103 slides here. If I do them all, we'll be here all night. Right. All right. So putting the sort of iterative hierarchy itself to one side, Cantor's view is that all of the mathematical domains that we deal with the exception of set theory, are all actual infinities. Right. Now, concerning the contemporary scene, then there's an interesting article by a guy named Newberg, Carl Georg George Newberg, on potential infinity, arguing against this is sort of contemporary scene, arguing against the idea, right? That the idea just doesn't make sense, right? But we'll take a look at Newberg now, right? So to gain a better understanding of the phrases X is potentially infinite, and T makes an assumption of the potentially infinite, I regard as a goal in itself. That is, he wants to try to make sense of these notions, right? One simply has to admit that they play an important role in both philosophy and investigations of the foundations of mathematics. My feeling, however, is that a clear meaning has never been given to them. So he suggests that we just haven't made sense yet of the notion of a potential infinity, right? Given that we already have a notion of actual infinity on the table, I think is what he has in mind there, right? He later adds, personally, I have no ordinary understanding of these phrases, potentially infinite, right? And I do not find much help in the existing literature on them, right? It seems that even examples are missing, right, of let's call this the merely potentially infinite, right? Those philosophers who are interested in the theme of the potentially infinite are usually drawn to it because they regard it as desirable to avoid assumptions of infinity. like contemporary or 20th century intuitionism, right, is probably the most prominent example of this, right? Yet they don't want to be restricted to a mere finitist position, right? Or, again, for that matter, Aristotle, right, doesn't want to claim that the universe is finite, right, but doesn't want the infinite either, right? An assumption of merely the potential infinity seems to be a way out of this quandary. It allows you to have your cake and eat it too, right? Don't have to buy into the metaphysics of infinity, of actual infinity, but don't have to be stuck with the finite either, right? But he argues that he says, well, I just have no way of making sense of this, right? Now he argues that on some straightforward attempts at definition, the potentially infinite just collapses into the actually infinite, or to the finite, right, depending on what the case at hand is, right? So what we cannot have, he claims, is a notion of the potentially infinite that's to be distinguished from both the finite and the actually infinite, right? So if we follow contemporary practice, as Newberg does, and of course we do, right? Again, people have asked me if I give this talk if I have any problem, or if we have any problem, Oystein and I, with actual infinity. The answer is no, of course, right? I shouldn't say of course not. Can't take anything for granted in philosophy. But no, right? We don't. We love mathematics as it is, right? We're not trying to revise it and think there's anything wrong with it. We're wondering if there is something else, right? So the very thing that Newberg says is missing, that's the thing that we're striving for, right? So if we follow contemporary practice and allow the actual infinity a place, right, as I want to, right, then there is no room for the merely potentially infinite. Everything is either finite or infinite. Nothing can fit in between those, right? Again, this is again back to Newberg, another chunk of it, or maybe it's the other article, I don't remember. So given the modern conception of sets in classical logic, I have never understood potentially infinite in a way which would give the potential infinite any use, a place of its own different from the finite and the infinite, right? All right, something that's sort of sitting in between, right? It seems to me that merely in intuitionistic frameworks, the predicate potentially infinite may find a reasonable reconstruction. Again, so maybe you don't know what that is, but intuitionistic mathematics is a type of mathematics which is meant to be sort of capture this idea, right? Among other things, right? Thus, in dealing with this discourse, that is intuitionism, I feel as if I were a Quinian linguist in the process of developing a radical translation from foreign language into his mother tongue. Right. Right. But he does concede, that is Newberg does, the following. It is granted that one could try to define X as potentially infinite by employing a modal vocabulary. Right. And notice we were giving modal talk, at least, of course, it was on purpose, but I was sort of noting the modal elements in Aristotle and Euclid. That's the plan here, right? That is, we hope to articulate a serviceable notion of the potentially infinite, one that could live side by side with the actually infinite. It'll play a role in understanding the notions of mathematical construction. We think in the notions of indefinite extensibility, an important notion on the table today, and in the debate over absolute generality, another topic on the agenda of philosophy nowadays. It will also, all right. Now, Newberg goes on to claim that at least since Quine's criticism, there is reasonable doubt as to the general understandability of the modal idiom, right? So Quine comes along, right, and says, and really doubts that we even know what modality is, right? He adds a note that when it comes to mathematics, he is Newberg, not Quine. Talk of possibility and necessity becomes dispensable since a mathematical sentence can be regarded as necessary if true, right? So that's going to be one of the puzzles, is try to make sense of that. I'm not going to make much headway on that. There's the intuition that mathematical statements are necessary if true, then why are we allowed to use modality to figure out what they mean? Right? Not going to be, I mean, we note the problem, but I'm not going to be able to do much with it today. Of course, it's incumbent on us to say something about the modality involved and to distinguish it from the sense in which every mathematical sentence is necessary if true. Right? All right, so our overarching aim in this paper, well, this project, this is getting away from us. It's more than a paper. Is to analyze the notion of potential infinity and assess its merits. And this leads to a number of more specific questions. Right? All right, so one of the more pressing ones is whether the conception of potential infinity can be explicated in a way that is both interesting, well, I'll leave it up to you to judge that, and substantially different from the now dominant conception of actual infinity. You might suspect that when metaphors and loose talk give way to precise definitions, the apparent differences will evaporate. That's what Newberg seems to be claiming. But of course, he doesn't want to use modality being a good Quinian. Right. As we'll explain, however, well, I don't know if we're going to be able to explain that today, right? But as I say, it's a big project. But there will be some differences, right? All right, maybe we can skip this. Another important, well, I keep saying that. Maybe we'll skip it and then I go on to talk about it. Concerns the relation between potential infinity and mathematical intuitionism. So more than anyone else today, intuitionists have continued to take the potentially infinite seriously, and they also insist that this requires revisions in the logic, right? In particular, the law of excluded middle has to be given up, right? So as a result of this, it's now commonly thought that the appropriate logic for potential infinity is intuitionistic, and that's what we're wondering, right? We don't think so, right? The reason why is because, well, I'm not saying the reason why people tend to think this is because potential infinity nowadays is only being articulated and defended by the intuitionists, who also articulate and defend, for related reasons, revisions in logic, right? Okay. All right, so our goal is to show that we have a coherent notion of potential infinity that's somehow, in some sense, sitting in between the finite and the absolutely infinite. Determine whether there's a connection between potential infinity and intuitionistic logic. There is, but it's more subtle. Might not get to that, so I thought I'd tell you now. And show that we can learn what we can learn from 2 millennia of theorizing about potential infinity. Okay. Okay. All right, so let's sort of get a little start on the modality. I'll explain the formulas as they come up if you're not familiar with them. Right. All right, so recall Aristotle's analysis of the, potentially infinite, but his analysis of the infinite, right? For generally, the infinite is as follows: there is always another and another to be taken, and the thing taken will always be finite, but always different. Right? Remember Sarabji's gloss on this, that infinity is the extended finite. Right, okay. So a nice example is Aristotle's claim that matter is infinitely divisible. Now, of course, we know nowadays it probably isn't, but again, got to sort of think as an Aristotelian, or as Aristotle did, that matter itself can be infinitely divided, right? And so consider a stick. However many times you divided the stick, it's always possible to divide it again. That's the thought, right? Now, it's very natural to explicate Aristotle's temporal vocabulary, right, over time in a modal way. This leads to the following analysis of the infinite divisibility of the stick, right? So the box there means it is necessary that, and the diamond means it is possible that, right? So some of you may have come across that, right? Okay. And the upside down A means for all, and the arrow means if then, right? Now I don't need to, you have it all, right? All right. So what this says is, and pxy means that x is a proper part of y. So x is part of y, but not all of it, right? So what this says is that this is the Aristotelian picture, that the stick is potentially infinitely divisible. Means necessarily for any proper part of the stick, if you have a part of the stick that's not the whole stick, that part has a proper part. Or sorry, that part could have a proper part. That's what the diamond is, right? So necessarily for every x, if x is a proper part of a stick, then there could be a part of that, a proper part of x. Right? Now, by contrast, if the divisions of the stick form an actual infinity, the following would hold. Just take out the box and the diamond, right? So, no, not necessarily, just plainly, for every x, if x is a part of a stick, then x has a proper part, right? That would be the contemporary picture, where we're thinking of the parts, the stick as just the sum of its parts, of its proper parts, right? The contemporary metaphysical picture, right? All right. So that would be for the stick. That would be what it is for the stick to be actually infinite, right? So according to Aristotle, that's not possible, right? For the stick to be actually infinite. It's not possible to complete infinitely many divisions of the stick. That is, now we have a formula now. It is not possible. It's not the case that it's possible that every part has a proper part. Every part has a proper part, right? So what we want to do is endorse 1 and 3, right? So here's 1. Necessarily, if you have a part of the stick, you could have a proper part of it, right? But it's not the case that every part does have a proper part. All right, now putting the metaphysics of sticks aside, right, and the physics of them, right, now we'll get to where I'm a little more comfortable. Again, I don't know what sticks are like really, right, but numbers, right, all right, natural numbers, right. So now consider the natural numbers, which according to Aristotle are also merely potentially infinite, right. Well, again, the exegesis here gets kind of tricky. I mean, it's not clear that numbers are actually objects for Aristotle. Number always means number of something, right? But put that aside. So we can express the potential infinity of the natural numbers as follows, right? So necessarily, for every number m, there could be a next number, right? That's what the successor is. It means the next number. So the successor of 6 is 7. The successor of 99 is 100, right? So necessarily, for any number, it's possible that that number has a successor. Or that number could have a successor, right? And that's the positive view. And the negative view is it's not the case that every number has a successor, right? So at any given time, there'll always be a largest number, right? But that number could have a larger number, right? So provided we're willing to use the resources of modal logic, there's no problem whatever in distinguishing the merely potentially infinite from the actual infinite, you know, which is, of course, what Newberg said. He said if they sometimes can use a modal vocabulary, right? Now, but there's going to be a problem of translation here, right? Most of the rest of the talk is going to be, well, maybe, no, not true. All right, forget that, the last thing. All right, so the use of modal logic introduces a problem of translation. Other than informal glosses or philosophical theses like today, the language of mathematics is relentlessly non-modal. And, well, not just today, I mean, you know, Hilbert's language is also non-modal, right? Euclid's wasn't. Actually, it was. It talked about what you could, I don't know, can't just sort of run through the whole thing in my head now to remember. He did talk about what you can do, but I don't know how much there was in terms of modality there. All right, but anyway, nowadays anyway, the language of mathematics, the official language in which it's formalized, there's no modality in there, right? In particular, when the question of the appropriate logic of potential infinity arises, it does so in the ordinary non-modal language of arithmetic. So what we'll need is some bridge between the modal language in which we're going to analyze potential infinity, you know, what we just did, and the ordinary non-modal language, right? How are we supposed to understand mathematical assertions, right? All right, the heart of the problem is that the existential quantifier, all right, so here's the claim. Oh, sorry, the heart of potentialism. So potentialism is the view that, or a view that the numbers only exist, that infinity is only potential. So natural numbers, at least some of them, only exist potentially, right? Most of them exist only potentially. So the heart of potentialism is that the existential quantifier of ordinary non-modal arithmetic, you know, so if you give the axioms for arithmetic, you're just going to say every number has a successor, right? So for any number, there's a next number, right? It's one of the standard axioms. The heart of potentialism is that you have to understand that modally. It has a potential, it's a potentiality to it. When a potentialist says that a number has a successor, she really means that it potentially has one, or it could have one, or it's possible to construct one, a successor, right? All right, so to be as neutral as possible on this, we're going to talk schematically about generating a successor, right? Right. So this suggests that the right translation of the existential quantifier, again, if you don't have any logic background, the backwards E means there is, exists, right? And the diamond means possible. So the right translation of the mathematical there is, you know, there is a successor, is there could be, right? And since the universal quantifier is hardly less restrictive, when we talk about all numbers, so we want to say all numbers have a successor, we don't just mean the numbers we've generated already, we mean all of them, the ones we ever will generate, right? So that so in effect, the right translation of the universal quantifier is that it should be a necessity in front of it, right? So the upside down A is the universal quantifier for all x. So when the mathematician says for all numbers, right, the way to gloss that is necessarily for all numbers, right? That is, no matter when they're generated, it'll have such and such properties, right? Right. All right. So now we can raise questions about which principles of the are valid, which modal principles are validated, right? All right, in the next section, we're going to defend a certain choice, namely the logic S4.2. I'll tell you enough about what that is if we have time. We probably have time for that. And then we can prove a highly desirable result that the modalized quantifiers behave logically like the ordinary ones, right? And that'll be the sort of last thing we'll do is that, right? But I think we have no, I'm going to skip this. Oh, yeah, a little bit of a philosophical interlude. Well, I mean, it's philosophical talk all along, so I don't know why I'm calling this an interlude, right? All right, so some theorists may object that potential infinity no longer looks very different from actual infinity. So I'm kind of getting ahead. So we're going to prove a mirroring theorem that that when you translate this way and you use the right modal logic, it all comes out the same, right? So so then you might think, well, then it just sounds like you're just doing mathematics as everyone else does it, right? In light of the classical version of the mirroring theorem, which is the last thing I'm going to do. So given that we can translate from the modal language to the non-modal one, and it's going to preserve all the properties, including the logic, the classical logic, then what difference do we have here, right? Now, that one conservative result is that we call it a conservative result. One can insist that despite the shared adherence to classical logic, if you in fact share that, the outline explication is nevertheless different. Because of not only because of the implicit presence of the modal operators, but also in the higher order logic. Again, I'm not going to get to that today, but that'd be sort of one result that matters. But again, that's further down the line. That's the next paper or the next book or something. But here's a more radical response, which I think we can talk about here. You might insist that if we're serious about the merely potential infinity, say the natural numbers, it's not enough to insist that every number be generated after finitely many steps, right? I mean, that's certainly necessary, but bad word given the modality here. You're certainly going to want that, but you're going to want more maybe. You might additionally require that every arithmetical truth is somehow be made true after finitely many steps in the process, right? So the thought might be, or one might think, that not only are the numbers merely potentially infinite, but any truth about them has to be made true in a finitary way, right? Again, I'll try to be, I think I can add a little bit of substance to this in a minute, but, well, it's not clear what this means, right? So again, if you're not sure, then, right, good. But perhaps we can illustrate the idea. So remember the strings, right, necessarily for all m, and possibly there is an m, express universally generalizations that at least seem to concern all the numbers, including ones not yet generated, right? So just stick to arithmetic now. So we're talking about natural numbers. So necessarily for every m, blah, 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 right, would be a statement about all numbers, not just all numbers we have now, but all the numbers we're ever going to have, right? No matter when they're generated. Now, what we're going to call the strict potentialist will not allow a generalization to be true merely in virtue of the space of possible worlds considered in its entirety, right? Not just because of all the instances, right? Rather, the generalization must be made true after finitely many steps in the process. In short, what we're calling the strict potentialist will insist that every question that has an answer gets the answer in a finitary manner, right? We should never have to wait till the end of time, right, to be able to answer a question about what we can generate, about a universally quantified sentence, right, about the numbers. Now, the distinction we have in mind here, can be illustrated with the so-called weak Browerian counterexample. So Brouwer was an early intuitionist, and early on he was arguing against the law of excluded middle, and that's what we're talking about here. So think about, well, first one is Goldbach's conjecture. So can an Aristotelian, right, or somebody who believes in potential infinity only, say now that it either is or is not the case that every even number greater than 2 is the sum of 2 primes? Right? That's the Goldbach conjecture. It's open, right? No one knows the answer now, right? So the Goldbach conjecture is for every even number greater than 2 is the sum of 2 primes, right? That's been verified as far as computers can verify, and proved for certain cases, but it's still open. All right, now can the potentialists say now that it's either true or false that every even number greater than 2 is the sum of 2 primes, no matter when generated, right? The only way we can know that would be to either generate a counterexample or run through all of them, right? Okay. But here's another example. This one is Brouwer's. So think about a real number now. Again, we normally talk about natural numbers, but think about a real number as like a decimal expansion, right? And think of the decimal expansion as itself potentially infinite, right? So like pi, 3.14159, as far as I remember, right? On, right? So think of a real number now as not as an infinite decimal like we do in contemporary terms, but think of this expansion itself as a potential infinity, right? So will there be at some point a string of 7 5s in a row in the decimal expansion of pi? Nobody knows, or if they do know, then change the number, right? Right. So is it the case that can we say now that there either is or isn't a string of 5 5s, or 7 5s rather, in the decimal expansion of pi? I think Brouwer used an example that eventually got refuted. It was like 3 4s in a row or something, but right. All right, now the classicist, someone who defends classical mathematics, will answer yes to both questions, right? Yes, because we're going to accept excluded middle, right? But from the point of view of potentialists, both questions assume that there are determinate facts about what is and what is not possible, right? That is, there are facts about the structure of possibilities, right? That's what would be involved there to answer yes to those questions, right? A strict potentialist, again, I'll define that view in a sec. We'll define that in a second, will demur from those instances of excluded middle. So for the strict potentialist, if the Goldbach conjecture or its negation is true, it must be made true after a finite period of generation, right? There has to be something that will eventually settle it one way or another if it's true. Well, of course, if it's false, then it will be generated in a finite, because we'll have a counterexample. But if it's true, something has to make it true, and that has to occur in a finite amount of time, right? Right. We can't just look at all the instances, right? Right. All right. So now, accordingly, we're going to distinguish 4 positions, 4 main orientations towards the infinite. So actualism, that's the contemporary view. That's Cantor. Actualism, well, that's Cantor minus the worry he has about the iterative hierarchy itself. Unreservedly accept actual infinities and finds no use for modal notions in mathematics, right? Perhaps the actualist will say that the existence of actual infinities is necessary, but again, that's as far as they're going to go, right, modally. The numbers exist in all worlds, all possible worlds, right? All right, that's character 1, the actualist, right? A second character asserts the possible existence of an actual infinity. We don't talk about that in the paper. I just threw it out because it's there, right? And somebody actually occupies that view, Jeffrey Hellman, a friend of mine, right? So this view asserts that it is possible for there to be an actual infinity, right? We'll not cover that one further and not even give it a name. But we might call it modal actualism or something like that. All right. Now, in contrast to these views, the potentialist asserts that the objects, all right, so now we've got 2 kinds of potentialism. Exerts that the objects of which mathematics is concerned are generated successively, such that at any one stage, right, of generation, there are never more than finitely many objects, but that we always have the ability to go on and generate more, right? Now, as hinted above, there are 2 versions of this view. The liberal potentialist holds that there are determinate facts about what is and what is not possible. So to repeat the above example, there is a fact of the matter concerning whether a counterexample of the Goldbach conjecture will ever be generated, right? And another fact of the matter about whether that 7 5s in a row will occur in the decimal expansion of pi. Right. So if the name weren't already taken, we might call this character a modal realist, right? But of course, those of you who are in the know that that name's already taken for this metaphysical view about possible worlds. But anyway, this character is a realist in truth value about modality. That is, the modal statements are made true objectively, right? But not about the existence of possible worlds, right? Which is where what the name modal realism is taken. So we just call it a liberal realist, liberal potentialist, right? Now, finally, the strict potentialist requires not only that every object be generated at some finite stage, but also that every truth be made true. Again, we need to figure out what that means, right? After some finite number of steps. We'll show that this loose talk, well, we won't show it in this paper because we won't have time, or sorry, I won't show it in this talk because I won't have time, but the loose talk about being made true can be made formally precise, and that the resulting version of strict potentialism can be satisfied. But it involves some of the techniques of an intuitionistic logic or realizability, which we won't be able to get into today. we'll find that this is where distinctively intuitionistic issues enter and where intuitionistic logic is appropriate. Right? So the question we raised before about whether the potentialist is committed to intuitionistic logic or classical logic, right, is decided here depending on whether they're strict or liberal. Right? For the liberal potentialist, the logic can be classical. For the strict one, it has to be intuitionistic. But again, that's something we argue for and won't get into anymore today. Right. All right. All right. I think we can. All right. So how am I doing on time? 15 more minutes?
10 also.
Okay. Good. Good. All right. So so what I want to do is sketch the modal framework for explicating the four positions, but at least some of them. So we're going to invoke the heuristic of possible worlds, right, to do this. So if you're not comfortable with this, then, well, too bad. I don't know of any other way to do it. But we understand this only as a heuristic, as a manner of speaking. The theory itself is formulated officially in the modal language with the modal operators primitive, right? They're not to be understood as quantification over possible worlds. We're just using the possible worlds talk as a heuristic, right? The framework takes its inspiration from another paper of Oystein's where he's developing the Cantorian idea, right? So the idea is, in the terms of the heuristic, is that all possible worlds are finite, but every possible world has access to ones with more objects in them, right? So from the perspective of the earlier world, the objects in the second only exist potentially. All right, there's different kinds of construction, which you could talk about: generating numbers, bisecting lines, putting, lines together to make figures and things like that. Right. Right. We'll also assume, without argument, this second paragraph here, that the objects are not destroyed in the process of construction. So every world, the objects in every world, if that world has access to another world, then all the objects in the first world exist in the second world as well. So objects don't get destroyed, only generated. So to use to paraphrase the Aristotle's title, we have generation but no corruption. Right? Don't lose objects as we go, but we generate new ones. Right? So that suggests for the modality that you're going to want the possible worlds to grow, or at least not decrease along the accessibility relation. So if a world W1 has access to world W2, then the domain of W1 will be a subset of the domain of W2, right? Objects don't go away, but new objects may have been constructed. We could make this a biconditional. It won't change the logic, but as weak as possible, just make it a conditional. Also, we want the object, clearly we want the relation to be reflexive. That is, every world has access to itself, right, in this context. That's just, where you don't construct anything, and it'll be transitive. So if I can get from here to here by constructing new stuff, and I can get from here to here by constructing new stuff, then I can get from here to here by constructing new stuff. Right? So those three together means that the logic is what's known as S4. Right? We also want the converse of the Barkin formula. That's here. So if it's the case that there is something which possibly has a certain property, then there could be something with that property. Right? You'll get that from the growing domains, right? So if there is something in a given world which has a certain property, which might have a certain property, right, then of course there could be, namely that thing, right? Because whatever world it has the property in, right, the object will exist there, right? So that means that the modality we want here is really probably not the ordinary notion of metaphysical modality. Again, we can get into that in the question period if you want, because that doesn't have that feature. There are objects which potentially have certain properties, but it doesn't mean that, like for example, I have the property that I might not have existed, right? If my parents had decided to do something else that fateful day 60-some years ago, I might not have existed, but it's not the case that there could be something that doesn't exist, right? Right. All right, but we're doing mathematical construction here, and so that principle is okay. But probably it's not going to be metaphysical modality as such. There are ways we can construct it out of metaphysical modality just by restricting, but just by restricting it in certain ways. All right. Let's see. So again, we're not going to get into as I said, and we don't have time to get into what modality is. There are a number of options on the market, which have been articulated various ways. All right, one more all right, so we already mentioned that it should be reflexive. Every world should see itself, and transitive. So we're going to get the logic S4, at least that. Where is that? Oh, but then there's another principle we have, which is not part of S4. So at any given stage in the process of construction, we may have a choice of which objects to generate, right? So there may be more than one thing you can do. Like in arithmetic, probably not, because if all you have are some numbers, all you can do is generate one more. But in geometry, you may have, say, 2 line segments, and I could bisect this one, or I can bisect this one, or I can bisect them both, right? So I may have a number of different things I could do. But all right, now suppose we're in a world where there's 2 different things we could do, and we do one of them, right, here, right? Well, and then we do something else, so we're over here, right? Now intuitively, the thing that I was supposed to be able to do here, namely bisect the second line, I should be able to do that here too, right? So if I can get from here to here by doing some construction, and I can get from here to here by doing some construction, then I could get from those 2 to a common place, right, by doing some construction, because all I would do is just do all the stuff over here that I did to get over here, right? And that would take me to a common, common top. So modal logics where you have that feature, it's called directed or generated. I forgot what they call it, but there's a name for that. And the logic they end up with is called S4.2, right? And so that's the logic that we adopt. The modal principle corresponding to that is this one. Again, I won't try to justify it. If something is possibly necessary, then it's necessary that it's possible, right? So that modal principle generates that kind of feature of the worlds where they have this sort of the directedness feature. All right. So I wanted to tell you about these 2 theorems that we have as quickly as I can. So remember, we're going to translate the universal quantifier as with the necessity in front of it, and the existential quantifier with a possibility in front of it. So you take an ordinary language in mathematics and put a necessity operator in front of all the universal quantifiers, and a possibility operator in front of all the existential quantifiers, leave everything else the same, right? You end up what we call the modal translation, right, of the formula. Okay, right. All right. Yeah, we'll call that the potentialist translation. Right. And okay. Now, a technical notion. We say a formula is stable if the following holds: that if it's true, it's necessarily true, and if it's false, it's necessarily false. So a stable formula is one that never changes its mind. Right. Now, intuitively, you would think that the atomic formulas are going to be stable, right, in this way. So if say in geometry, if you have one line segment that's a part of another one, then nothing you can do is going to change that, right? And if you have one line segment that's not a part of another one, nothing you can do to, would change that, right? So we can give the first of the mirroring theorems now. So start with the notion of of an ordinary language of arithmetic, a classical language with classical logic. And call that the turnstile means, that the thing on the right is deducible from the thing on the left. And then deducible diamond means that it's deducible with the same logic in the modal language with S4.2 and axioms that all the atomic predicates are stable, right, in that sense before. And the mirroring theorem is this, that for any formulas, if you can prove in the non-modal language that it follows, then you could prove the modal counterpart in the modal language, which consists of the original theory plus the modal logic S4.2 plus the stability of the atomics, right? Right. And then there's a second. All right. So this mirroring theorem tells us that if we're interested in classical logical relations, with excluded middle, then it suffices just to drop all the boxes and diamonds. That was sort of what led to the nervousness that, well, then it looks like we just got the same mathematics we had all along. And at least so far you do. I mean, there are differences that'll show up later, but at least so far you do. The other mirroring theorem is an intuitionistic version of it. And the only difference there is that you have to assume that all of the atomics are what are called decidable, excluded middle holds for them, and then you get essentially the same result. All right, good. So I think I've used up my time, so this is a good place to stop.
Okay,
Right,
well,
right.
thank you very much.